Is there is there anything more to do there? No, because the derivative of the inner argument with respect to x is just 1. So the chain rule doesn't give us anything further to do there. The second order y derivative, dy of df dy, well, for this we're going to have to use the product rule. Okay, first of all, so it's minus 2y times the sign of the bracket. So applying the product rule, it's going to be minus 2 times the sign of the bracket. And then minus 2y again, this time times the derivative of the sign of the bracket. And the derivative of the sign of the bracket is cosine of x plus y squared. And we pick up another factor of 2y from doing the chain rule. So that's by a combination of the product rule and chain rule. If we indicate the rules, and the reader can tell, as long as we've done it correctly, that we're correctly applying the rules there. So it's the product rule on this because it's a function of y times another function of y. So first of all, we held the sign of the bracket the same and differentiated the 2y, so it differentiates to 2, minus sign in front. And then you held the minus 2y the same and differentiated the sign of the bracket. And that requires the chain rule, so it's going to be cosine of x plus y squared by 2y, because we're all the time differentiating with respect to y then. And maybe just tidy that up a bit, so it's minus 2 times the sign of the bracket minus 4y squared times the cosine of the bracket. And just remember to double check you're handling your positive and negative signs correctly and keeping accounting for all of those. Okay, so now we just have the third mixed second order partial derivative to take. So we need d2f dx dy, and we'll indicate that as the x derivative of the y derivative. The y derivative we have just at the top of the screen there. So we're differentiating that with respect to x now. So it's going to be minus 2y times the cosine of x plus y squared. With nothing further required from the chain rule because the derivative, because see the differentiation we're carrying out here is with respect to x. So the derivative of the sign of the bracket is just going to be cosine of the bracket. Okay. So that more or less is all that's required for part A. I think that would get you full marks there. And remember to quote the significant properties of differentiation as you're using them. Yeah, chain rule and product rule and so on. Part B. Okay, so part B, well, first of all, we should just take the time to read it carefully because you're given a fair amount of information in it. So it says, use the results from part A. Okay, so we'll be making use of the derivatives we have from part A. To get the second order Taylor polynomial approximation to the function f. So we're talking about the same function f. The second order Taylor polynomial approximation will be a polynomial of order 2, with constants, x and y terms, x squareds and y squareds and xy terms, that approximates the value of the function. Okay. You're given the formula. You're given the formula for the Taylor series here. We recognize here that it's an expansion about the origin because the derivatives or the derivative operators are always evaluated at the origin, 0, 0. We're only going up to order 2. And we're reminded here on the expression for the differential operator capital D. Okay, it's h d dx plus k d dy. Where h and k are respectively the small variations in the variables x and y off the origin. Okay, and we're given the final answer, so we'll, if we reach that, we can be fairly confident that we've worked correctly. Okay. So what can we say here? Yeah. So I guess what we've got to demonstrate here is we understand what the formula is actually going to look like. So we can say expanding the given formula for the Taylor polynomial gives, so we're evaluating f at a point close to the origin. Well, I'll just repeat the formula just for completeness. Okay, but I just want to expand this out now, so I see clearly the various parts of it. Okay, the whole thing is an approximation, but now I'm exactly expanding the sum. So the zeroth term is 1 over 0 factorial by convention. 0 factorial is declared to be 1. So, and you've got d to the power 0 applied to f evaluated at the origin. Now, what is d to the power 0? D is a differential operator. An operator to the power 0 means the operator applied no times, means the identity operator. So d to the power 0 applied to f is just f. So all of that together, the n equals 0 term is simply f at 0, 0. Okay, it's just the origin, it's the function evaluated at the origin. And that's the 0th order approximation to something. If somebody asks you what's the value of the function close to the origin, you know, the naive kind of approximation you give is just exactly the value at the origin. Yeah. If you ask me to predict what the weather is going to be like tomorrow, I'll just say it's going to be like the weather today. It's the first stab at a guess, the least information guess. And so then the n equals 1 term, just get a bit more sophisticated. So when n is equal to 1, we're talking about 1 over 1 factorial. Again, that's just 1. And then d applied to f. Okay. So that will simply be h times df dx plus k times df dy. As n equals 1 term. Then the n equals 2 term will be 1 over 2 factorial, which is a half. And then d squared applied to f. And d squared applied to f, remember d is an operator, so that's d of f. So we've got h d dx of all of this plus k d dy of all of this. Okay. So what that amounts to is going to be the quantity h squared times d2f dx squared plus k squared times d2f dy squared plus 2 times hk times the mixed second order partial derivative. Okay. So that quantity there in the brackets is d squared applied to f. Okay. And I haven't indicated the evaluations. I mean, you could put a kind of bar and a subscript against each thing, but it would kind of litter up the expression. So I'll just say all derivatives evaluated. All derivatives evaluated at 0, 0. Okay. So we need to do that to see explicitly what the polynomial is going to be. So this thing is clearly going to be a polynomial in h and k, and it's going up to order 2. The highest order terms are order 2, order 2, order 2. So we just simply need to evaluate the coefficients. Right? Evaluate f, the first order derivatives, and the second order derivatives. And we have those from our work in part A. So what is f of 0, 0? Well, it's cosine of 0, so it's 1. H times df dx. So let's write all these in. Well, df dx is minus the sine of x plus y squared. So df dx evaluated at the origin is a sine of 0, so that's 0. And you've got a k times df dy. Df dy is sine of x plus y squared times 2y evaluate that at the origin. Well, it's got a factor of y in it, so it has to be 0. Okay. Then we've got a half times h squared multiplied by something, d2f dx squared. Again, that's cosine, so it's minus the cosine of x plus y squared. That's going to be minus 1 this time. No. Yeah. Minus the cosine of 0, minus 1. K squared times something is d2f dy squared. It's just there. Top of the screen, d2f dy squared is this function here. So what do you get when you evaluate that? At the origin, 0, 0, sine of 0, 0, and there's a factor of y squared. So it's going to be 0 again. So the whole thing is going to be 0. And then you've got 2hk multiplied by something d2f dx dy evaluated at 0. This function here. But when you evaluate that at the origin, it's got a factor of y in it. So it's going to be 0. So most of that is 0, but again, we've laid it out in such a way that it's clear that we've evaluated each term. Or we could just put a little comment here: evaluating using the results of part A. So the only thing that survives is 1 minus a half times h squared. As required. That was the correct polynomial given in the question. Okay. Is that okay? Any queries about that? The crucial thing to get right is the correct treatment of the powers of the operator. Yeah, if you're asked to go up to d cubed or d4, it would be the corresponding cubic and order 4 polynomial. Okay, but don't forget about all the possible cross product terms in the power of the operator. I've seen people, for instance, declare that the operator d squared applied to f is just these two. Well, that's a bit careless. It's not taking account of all the partial derivatives that occur when you do d of f. Okay. Okay. So part C then. Part C is asking you to derive one of the most important properties of the Laplace transform as related to the way it's used to solve differential equations. So this is a standard proof from the notes. So we seek the Laplace transform of the derivative of g. And the expression we're going for is an expression involving the Laplace transform of g. So we begin with the definition of the Laplace transform. The definition of the Laplace transform is this. It's the integral from 0 to infinity of the exponential function e to the minus st multiplied by whatever you're taking the transform of. Okay. So the other bit there is dg dt. Now, what can we do with this? We don't have any specific function g. We're just working generally here. But what we can refer to is the Laplace transform of g. Then we also look at this integral. What possible things can we do with this integral? Well, the integral is set up nicely for integration by parts, okay? Because it's a product of two factors, one of which is a derivative, and we're able to differentiate the other one as well. So think it's fairly clear that to treat that integral a little bit, we could do integration by parts. And that will produce for us an integral involving the function g. And that's where we're going to get our Laplace transform of g from. So applying integration by parts here, this will give me, okay, the product of the two things, so e to the minus st times g of t, evaluated at 0 and infinity, and then minus the integral of the derivative of the exponential this time, the minus s e to the minus st times the undifferentiated function g. So that's comes from applying integration by parts. Okay, so what comes from this? Well, well, in the integral, treating the integral is the most direct thing to do. See, the integral is with respect to t, so s is an independent variable from t, so this s can slide outside. So this is going to give us plus s times the integral from 0 to infinity e to the minus st times g of t dt. And that integral we recognize as, of course, the Laplace transform of g. Treating the other part here, well, it's going to be the limit as t goes to infinity of the quantity e to the minus st g of t minus this thing evaluated at 0. So e to the 0 is 1. This is going to be simply minus g of 0. And we can say that this limit t goes to infinity of e to the minus st g of t, this is equal to 0 since g has a Laplace transform when we first introduced the Laplace transform, we talked about this briefly, but the Laplace transforms don't necessarily exist for every possible function g. But as long as the function g isn't too wild, as long as you can integrate the function g, and as long as it's eventually dominated by some kind of exponential function. Remember, the exponential functions grow extremely quickly, or an exponential to a negative t will decay very quickly. So as long as that decay induced by the exponential factor eventually it dominates any behavior in g, that limit is going to be 0. Okay. Because we're assuming that g has a Laplace transform, we know that this is going to be the case. Okay. So if that's just a comment there, continuing the equation gives us 0 minus g of 0 plus s times, and then we recognize that integral as the Laplace transform of g. Okay, and that's the required result. Okay. So, are there any questions about that? So there's 3 other questions, questions 3, 4, and 5. We did the Fourier series stuff quite recently, so I'm tempted to look at questions 3 and 4. Any preference over questions 3 and 4? 4? Any other votes? Questions 3 or 4? Got 1 vote for 4, so maybe go for that. So 4 then is the is the longer question then on the Laplace transform methods. And it's a kind of an integrated question. All the parts relate to each other. So first of all, we're presented with this piecewise linear function f. 0 outside the interval 0 to 4. And in the interval 0 to 4, it does this triangle behavior. And we want to explain how the function is represented as a combination of Heaviside step functions like this. We want to explain it. So that will require defining what the Heaviside step function is, indicating any of its necessary properties, and then showing that we can express f as that combination of Heavisides. Then part B is to show, making use of results from the table on Laplace transforms, is to show what the transform of that function f is. Then finally, in part C, we're asked to solve this second order ODE, d2y dt squared plus 9 times y equals 27 times f, this same function f here. So we're making use of f in all three parts there. Okay. So let's have a go. Let's have a go at this. Okay, so what I would do first is introduce the Heaviside step function. Okay. So I'd say the Heaviside step function h of t is defined as, so just very quickly demonstrate that you know the definition of h of t. It's this 0, 1 function. It's the switch, which is switched off all points in the past until at time 0 it switches on. It stays on forevermore. And if we've got two quantities A and B, then the combination h of t minus A minus h of t minus B is the switch function this switch function, so we'll just indicate what it is here. It's the function that's switched on between A and B, and it's off otherwise. Yeah. Just kind of sketch a quick graph of that. Got A, got B. Then you see, for all early values of t, for all values of t less than A, both arguments to the Heavisides are negative. And h, as we see from our definition, h on a negative quantity is 0. So the function is always 0 there. But then as soon as t passes A, this first argument becomes positive. So that's equal to 1. But the second argument is still negative, because you're still, t is still less than B. So that's 0. So you got 1 minus 0, so you got 1. So that gives you this 1 value as soon as t passes A. And those conditions are held until t passes B. And once t passes B, both arguments are positive. So both Heavisides give you the value 1. So you just got 1 minus 1, so you got 0. And that's the situation for forevermore. So it's equal to 1 between A and B. And then it's back to 0. Back to 0 then outside of that interval. So that's enough on the Heaviside, introducing the Heaviside. That gives us what we need in order to turn f into a combination of Heavisides. Okay. So coming back to our function f, so this is 0, 2, 4. This is height 2. So we can express f as f is the sum of these two functions, f1 plus f2. So f1 is going to be the function that between 0 and 2 is this first line, the left line, and 0 elsewhere. And f2 is going to be the function which is 0 everywhere except between 2 and 4, it's this line here. So f1 is going to be between 0 and 2, it's going to be this line, and that's just the line t. Sorry, this is f1 of t. That's going to be 0 otherwise. So I'm setting it up as something that I can apply this switch function to. And the function f2 of t is going to be non-zero between 2 and 4. 0 otherwise. Then we just need the equation of that line then. And so that's the line of slope -1, it's going to be minus t, and it's got intercept 4, so minus t plus 4. Okay. So using the Heaviside switch combination, we get that f1 of t, well, it's this switch here for the values 0 and 2, so it's h of t minus h of t minus 2, and well, that gives me the quantity 1, but I want the quantity t, so I better multiply all of that by t. So that's f1. The combination of Heavisides is switched on in the relevant interval and switched off otherwise. And that's what we want from f1. Switch on this function t, so I multiply the switch by t, and switched off otherwise. And f2, evaluated at t, well, the switching interval here is 2 to 4, so it's going to be h of t minus 2 minus h of t minus 4. And the quantity I want to switch on is minus t plus 4. Does that make sense? Any queries on that, or things I could clarify on that? So there's my two expressions for f1 and f2. So now I simply add them together to get f. So I get f of t here, and adding them together here, I'll have t, h of t, and then I've got h of t minus 2's here. So I get a minus t minus another t, so it's minus 2t plus 4. I can actually express that as minus 2 times t minus 2. That gives me minus 2t plus 4. And that's multiplying h of t minus 2. And then I've got minus, I'll express it this way, it's a minus sign multiplied into minus t plus 4. So it's going to be plus t minus 4, h of t minus 4. That's required. How many marks is going to be? 6 marks going to be. Okay. Yeah, but it's good to get the definition of the Heaviside at the start, show the that switching construction, and then show how it applies to your function f. So then in part B, we want to find an expression for the Laplace transform of f. So There's a property on the table when you look it up. It's a property that tells you how to transform a product of the Heaviside and some other function, as long as it's set up appropriately like this, that both the Heaviside and the other function are evaluated at the same shifted argument, t minus a. And that's indeed the case here that we've ended up with. We've got products of functions and Heaviside where both the functions are evaluated at the same shifted argument. Okay. Now the results from the table, this is e to the minus as, is it? Times the Laplace transform of g of the unshifted version of g. Just the Laplace transform of g of t. Just about 90% sure that's a minus sign, maybe it's a plus sign. Pretty sure it's a minus sign. 95% sure. Minus sign. Okay, so that's on the table. So we're going to apply it now. And what's the function g that's happening here? Well, really it's the same. It's always the function g of t equals t. G of t equals t evaluated at t. G of t equals t, but evaluated at t minus 2. T minus 2, and then there's a coefficient of minus 2 in front of it. And then plus g of t equals t, but evaluated this time at t minus 4. So first using linearity, we get that the Laplace transform of f of t is the Laplace transform of this thing, t h of t, minus 2 times the Laplace transform of t minus 2, h of t minus 2, and then finally the Laplace transform of t plus 4, t minus 4, h of t minus 4. So first I'm just indicating the use of linearity to say the Laplace transform of f is this. Is the sum of the 3 individual Laplace transforms, and the minus 2 coefficient slides out.
Is it t minus 2?
T minus 2, yeah, sorry. Just from the same thing from the top. Okay, each of these now are fully set up there for applying this. They've got different values of a, but it's always the same function g. So notice the same function g of t equals t used in each of the 3 terms. Okay, but just a different value of a each time. So here it's a equals 0, so we simply have e to the 0s. Maybe just 1. Here we have minus 2 times e with a equals 2, so e to the minus 2s. And here we have e to the minus 4s. So those are all multiplied by the Laplace transform of the quantity t. Okay, the Laplace transform of the unshifted function, g of t. Well, it's just the function g of t equals t. So that's 1 minus minus 2 e to the minus 2s plus e to the minus 4s. And the Laplace transform of t is 1 over s squared. That does, it mightn't be especially useful, but that does factorize as 1 minus e to the minus 2s squared all over s squared. but we mightn't ever want to use that expression. I think when we come to take the inverse transform, we'll probably want to make use of the linearity to apply it to the expanded polynomial. Yeah, so that's what was asked for in part B, get the Laplace transform. So I'll continue this evening. We'll continue with part C, and we'll see what else we can put in there this evening as well. Okay. Thanks for your attention, and I'll see you later on.